So today I would like to give a lecture on combinational logic circuits. So what is a combinational logic circuit? It is that digital circuit whose output depends only upon the current inputs. So if there are any changes made to the current inputs, we see an immediate change in its output. That's a combinational logic circuit. One of the basic combinational logic circuits is the adder. So these are all arithmetic circuits which performs all the arithmetic operations. So let's first look into the basic combinational logic circuit, that is a half adder followed by a half subtractor, and then once we get hold of half adder and a subtractor, we can analyze the design of a full adder and a full subtractor, followed by carry ripple adders and carry look ahead adders. So what's a half adder? Half adder is a very basic combinational circuit which adds two single bit binary numbers and it produces two outputs, that is sum and the carry out. One of the main or the important thing to note about half adder is that it doesn't consider the carry from the previous sum. So the operation performed here is half addition, and the circuit which is used to realize it is called a half adder. So let's now analyze the truth table of a half adder. As I said, it adds two single bit binary numbers. So let me call it as x and y. And it generates two outputs, sum and a carry out. So each bit is added to generate the sum. Addition is more like an arithmetic operation performed. Basic arithmetic operation. So 0 plus 0 gives out a sum 0 without a carry. 0 plus 1 gives the sum as 1 without a carry. 1 plus 0 gives the sum as 1 without a carry. 1 plus 1. This is a special case. 1 plus 1 is nothing but 2 in decimal. So if I convert 2 into binary, I get 1 and 0. So in which sum is 0 and the carry out being generated is 1. This is just a block diagram of a half adder. So we can now draw the expression for sum and carry out with the help of a truth table itself. It can also be done with the help of a K-map using a 4-cell K-map, but I think truth table is sufficient enough to draw its expression. So what is sum equal to? Sum is high in these two places, that is when x is 0, y is 1, or x is 1 and y is 0. So we can now get the Boolean expression for sum as x bar y plus x y bar, which is nothing but x or y. And how about carry out? Carry out is high whenever x is 1, y is 1. That means C out can be expressed as x into y. We can now draw the logic diagram of sum and C out, where sum is expressed in terms of XOR, so a 2-input XOR gate is sufficient enough to draw the sum. And then we have a 2-input AND gate which multiplies x into y and gives out C out. So this is about a half adder. Now we'll move on to half subtractor, which is more similar to a half adder, but only difference is that it performs subtraction and produces the difference and the borrow out. So subtracting a single bit binary value y from another value x is done with the help of a half subtractor to produce a difference bit d and a borrow bit b out. And this operation is called half subtraction, and the circuit which is used to realize it is called a half subtractor. Let's look into the truth table of a half subtractor. So two single bit binary numbers are subtracted to get the difference. So 0 minus 0 gives me a difference of 0 and there is no requirement to borrow a bit. Then the second case is a special case here wherein we have to subtract 1 from a 0. So we are subtracting a higher number from a smaller value. So there will be a requirement for a borrow out. So we'll borrow a bit. In that case, my x value will now be 1, 0. 1, 0 minus 1 gives me a difference of 1. So 1, 0 is nothing but 2 in decimal. 2 minus 1 is 1. Very simple. I guess you were able to analyze it. So when x is 1 and y is 0, the difference is 1 without a borrow. 1 minus 1 is very simple. Difference is 0 without a borrow. This is just a block diagram of a half subtractor. So let's draw the Boolean expression for difference and borrow out. So difference is high in these two cases, similar to what we saw in sum under half adder. So difference is equal to x XOR y, and borrow out is high when x is 0 and y is 1. So x bar y is the product term for borrow out. So we can now draw the logical diagram using a 2-input XOR gate giving out the difference, and an additional gate used here is an inverter because x value must be inverted and sent in as an input to the AND gate. So x bar into y gives out the borrow out. So this is about half adder and half subtractor. So we'll now move on to a full adder circuit. So full adder circuit can also be constructed using two half adders, or else we can analyze it separately. So here full adder will consider the carry from the previous sum. So in this case we have three inputs, x, y and carry in. So 3 inputs means how many combinations? 2 power 3 combinations starting from 0 to 7. So total 8 combinations can be drawn for the inputs x, y and cin. So each bit is added to generate the sum and the carry out. 0 plus 0 plus 0 gives the sum as 0, C out as 0. 0 plus 0 plus 1 gives the sum as 1 and C out as 0. 0 plus 1 plus 0 gives out the sum as 1, carry out as 0. Now, we have to add these 3 bits, 0 plus 1, which gives out the sum 0 and a carry out as 1. So this is more similar to the last row of a half adder. Then, we have 1, 0 added together to generate a sum 1 and C out as 0. So 1 plus 0 plus 1 gives me a sum of 0 and a carry as 1. A carry is generated when you have 2 bits, 2 values as 1 and 1. Again the same case with the last but one row. And then let's move on to the last row wherein all the 3 inputs are high. 1 plus 1 plus 1 is nothing but 3 in decimal, and if we express it in binary we get 1 and 1. So sum is 1, carry out is 1. So with the help of a K-map, it will be easier for us to draw the expression for a full adder. So as we see in this, we have to use a 8-cell K-map as we have 3 inputs. So Cin against xy is drawn here, and we see alternate cells consisting of ones, right? So this is more like a chessboard. So I cannot group ones, this one with any of the others to get a simplified expression. So each one of the ones in the cells are isolated. So I end up getting this expression where S is equal to x bar y bar into Cin plus xy bar into Cin bar plus xy bar into Cin bar plus xy Cin. So if we further simplify it, we can express it in terms of the XOR operation wherein S is equal to x XOR y XOR Cin. So remember, whenever you see a K-map with a chessboard kind of a thing, it can easily be expressed using XOR gates. Then the carry out is drawn here, and the expression for the carry out is xy plus xin plus ycin. This is about a full adder. So in our next lecture, we will discuss about full subtractor, ripple adder and a carry lookup adder, and we will see how a ripple adder and a carry lookup adder differ each other and which is advantageous over what. Thank you.